For my standard 3.1, I chose to do problem 3.4 from our textbook. It says consider a spin 1/2 particle with magnetic moment placed in a uniform magnetic field aligned with the z-axis. Verify by explicit matrix calculations that the Hamiltonian commutes with the spin component operator in the z direction but not with the spin component operators in the x and y directions. Comment on the relevance of these results to spin precession. So first thing I did to solve this problem is I wrote down our spin operators in the x, y, and z directions, and you can just get these in chapter 2 from our textbook, and they're shown right here. And I got the definition of a commutator from chapter 2 in our textbook, and it's just if a and b are operators, they will commute if this, or two operators commute if this equation is equal to 0, and if they're not equal to 0, then they say they don't commute. So next thing I wanted to do was derive our Hamiltonian for this situation and write it in matrix representation. So we can write our magnetic field in the z direction, or our magnetic field is in the z direction, so we can write it as this. And then we can use our definition of a Hamiltonian. So it's equation 3.23 in our textbook, and it's H is equal to E over mass electron, and then our spin vector dotted with our magnetic field vector. So using our definition of a magnetic field, which we have right here, our Hamiltonian becomes H equals E times B naught over mass electron times SC, and that's our spin operator for SC, or in the z direction. And we can use our definition for omega naught, which is E times B naught over mass electron, and rewrite this as omega naught times S sub z. The Hamiltonian we have written is proportional to the SC operator, so H and SZ will commute and thus share common eigenstates. Now we can write our Hamiltonian as a matrix in the SC matrix representation. We have H, we have this. So now we can check commutation for our operators in the x, y, and z direction. So first, we already know that S sub z will commute, but it wants us to explicitly check it. So here is me going through the steps. So this is our Hamiltonian. Here's our spin operator in z direction. Using the definition of a commutator, we write this and then plug in our matrix representations, and we just go through basic matrix multiplication and matrix subtraction. We find that this equals 0. So we know from our definition of a commutator that if it's equal to 0, then two operators will commute. So since this equals 0, then H and S, the spin operators for Z, do commute. And then next, we have to check SY and the spin operators for Y and X directions don't commute with the Hamiltonian, so that means that they're not, the commutator for those are not going to equal 0. So here's spin operator for Y. Do the same thing. Do some matrix multiplication, some matrix subtraction. We find that it does not equal 0. So these two operators do not commute. And finally, S sub x, or the spin operator in the x direction, that's supposed to be an x. Going through the same steps, matrix multiplication, matrix subtraction, we find that this is not equal to 0, so these two operators do not commute. And this is my standard 3.1.